You know the feeling. You've got a super sensitive signal cable. You wrap it in this high-quality, expensive, conductive shield, you ground it perfectly, and then you just watch your system completely fail its electromagnetic compatibility, or EMC tests, because of low-frequency magnetic noise. It's incredibly frustrating, right? Well, if you're relying purely on the material of your shield to block magnetic fields, you're actually setting your hardware up for failure. Welcome to The Explainer. I'm your host, and today we're going to tear down one of the most pervasive myths in electrical engineering. So, why does this happen? Well, by the end of this explainer, you're going to master a totally counterintuitive physical reality. Protecting a circuit from low-frequency magnetic noise has almost nothing to do with the metallic properties of your shield. It's actually entirely dictated by your circuit geometry. We're going to look past the surface of the cable, dive straight into the physics, and arm you with the exact intuition you need to solve this. Okay, let's dive into this. Mastering this specific concept isn't just an academic exercise. It's absolutely critical for robust hardware design. Because if you don't understand the physical reality of how magnetic fields couple into conductors, you're just going to waste time and money adding heavy, useless shielding to your products. And worse, you'll face disastrous compliance failures when your prototypes finally hit the EMC lab. Here is our roadmap for today. 1. The core concept. 2. The math. 3. The 50 kilohertz walkthrough. 4. The grounding pitfall. And 5. Our EMC survival summary. Let's start right off with Section 1, the core concept, understanding loop area. To really understand how magnetic coupling happens, we need to zoom in way past the outer jacket of your cable and look directly at the invisible routing of the current itself. You see, the foundational theory of magnetic shielding revolves around one single metric, and that's the loop area. Simply put, this is the total physical area enclosed by the forward current flow and its actual return path. Here is the never-forget analogy for this rule. Imagine a low-frequency magnetic field as a relentless howling wind. Your circuit's loop area is a butterfly net. If you want to catch less wind, you don't go and change the material of the net's mesh. No, you have to physically shrink the size of the hoop. Shrinking the net is literally the only way to catch less wind. Now let's map this wind net analogy directly to reality using Henry Ott's principles. Take a look at the unshielded circuit on the far left. The current flows out through the top wire and returns way down at the ground plane. That enclosed rectangular area? It's massive. It's a giant butterfly net catching all that magnetic wind. Now look at the middle setup. We added a non-magnetic shield and grounded it at both ends. If the frequency is high enough, specifically greater than 5 times the shield's cutoff frequency, the return current naturally wants to flow back right through that shield, directly next to the source wire. So what just happened here? We physically collapsed the distance between the forward and return paths. We shrunk the butterfly net. The shield isn't magically blocking the magnetic field, it's physically redirecting the return current to reduce the loop area. Moving on to Section 2, the math, rules of physics. Notice how systematically the physics build here. Step 1, an alternating current in a source wire creates a magnetic flux. Step 2, that flux links into our receptor circuit based on a geometric property called mutual inductance. And finally, Step 3, by Faraday's law, that changing flux induces a noise voltage directly in our circuit. And here is the exact mathematical expression governing this whole interaction. Let's break this down completely so it really sticks. V sub n is our induced noise voltage. This is the physical interference threatening our signal. It equals J times omega times m sub 12 times I sub 1. Let's look at the terms. The J is the imaginary unit, which simply tells us there's a 90-degree phase shift between the source current and the noise voltage. Omega is the angular frequency, equal to 2 times pi times the frequency. This means the noise voltage scales linearly with frequency. I sub 1 is just the raw current of the interfering source. But the absolute most important variable in this entire equation is m sub 12. This is the mutual inductance between the source circuit 1 and our receptor circuit 2. M sub 12 represents our loop area. It's pure geometry. If we shrink the loop area, our butterfly net, m sub 12 drops towards 0, and the noise voltage V sub n drops towards 0 right along with it. Which brings us to Section 3, the 50 kilohertz walkthrough, experimental proof. Math is beautiful, sure, but engineering requires empirical proof. So let's plug some real numbers into our mental model. Here we have an actual experimental setup. There's an interfering source loop generating a 50 kilohertz magnetic field, and we're measuring the noise picked up by different test cables. Now, you might be wondering why 50 kilohertz? Well, because at 50 kilohertz, the frequency is greater than 5 times the shield cutoff frequency for these specific cables. This means the return current physically wants to follow the path of least impedance, which is straight through the shield if we actually give it the chance to do so. And this brilliantly illustrates our equation in action. Let's solve this mentally. Circuit A is our unshielded baseline. The return current takes the distant ground plane. M sub 12 is massive, so the noise voltage V sub n is massive. Result? We get 0 decibels of attenuation. Nothing. Now look at circuit C. We add a shield and ground both ends. The return current splits, and some of it flows through the shield right next to the inner conductor. Our loop area shrinks. M sub 12 decreases, the noise voltage drops, and we achieve 27 decibels of attenuation. Not bad. But look at circuit G. This is a true coaxial arrangement. The shield is the dedicated return path. The return current flows perfectly and uniformly around the center conductor. Our geometric loop area and therefore our mutual inductance, M sub 12, drops to practically 0. And just as the math predicted, our noise voltage gets completely obliterated, giving us a staggering 80 decibels of attenuation. The math absolutely works. Next up, section 4, the grounding pitfall, a critical error. But here is where designs fill out in the wild. The crucial point is this major gotcha that constantly trips up junior engineers. Look at the configuration on the right. You paid for a premium shielded cable. You wrapped your wire in it, but worried about electric ground loops, you grounded the shield at only one end. Well, because the shield is floating at the far end, no return current can physically flow through it. The current is forced to return all the way down through the distant ground plane. Your loop area hasn't changed by a single millimeter. M sub 12 remains massive. Your noise voltage remains entirely unmitigated. By grounding the shield at only one end, you've achieved exactly 0 magnetic protection. Finally, section 5, survival summary, EMC key takeaways. Let's bring this all together so you can deploy it in your next design review. Here is your rapid-fire survival summary. Number 1. For low-frequency magnetic fields, shielding equals loop area reduction. Remember the butterfly net. Number 2, the equation V sub n equals jωM₁₂I₁ governs your noise profile. Shrink the geometry, shrink the mutual inductance, you kill the noise. Number 3, single-ended shield grounding forces current into the ground plane, offering absolutely 0 magnetic protection. Henry Ott dedicated his legendary book with this fantastic quote from Albert Einstein: "Everything should be made as simple as possible, but no simpler." We didn't skip the math today because, well, the math is the physical reality. Master the geometry and you will master EMC. If you found this technical deep dive valuable, hit subscribe for more EMC and automotive communication protocol survival guides. Keep your loops tight. But before you go, I want you to ask yourself, if shrinking the loop area is this critical at 50 kilohertz, what do you think happens to our math when we push our signals into the gigahertz range? Think about it, and I'll see you in the next explainer.